Swayam Prabha. Digital India. Educated India.
Just join. So I'm going to teach you the Markov chain Monte Carlo, the method of the Bayesian, under the Bayesian methods. It's a very powerful technique, which gives you a very scientific way of generating samples. What do you mean by generating samples? Yesterday we saw a problem, right? So Suraj also demonstrated. We wanted to find out the Q, the heat flux from the set of temperatures in a slab. So we just divided the Q from 500 to 1500 or whatever in steps of 100. And then it was pre-assigned, it was arbitrary. Okay. The bounds can be decided based on prior experience, but these divisions were arbitrary. And for each of these points, you found out you ran the forward model, got the simulated temperatures compared to the experimental temperatures, got a e to the power of minus chi square by 2, put your prior blah 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 whatever. But there should be a more scientific way of generating these samples. So one is important class of methods is basically the Monte Carlo methods. The Monte Carlo method starts like this. It is an iterative method. So you generate a sample for Q. You generate a sample for Q1. Let's say the first sample is Q1. The second sample Q2 depends only on Q1. Okay, what do you mean by that? The third sample Q3 has got no relation with Q1. That means Q1 is generated from Q2 is generated from Q1 randomly. Q3 is generated from Q2 randomly following some distribution. This distribution could be a uniform distribution, Gaussian, and so on. I'll teach that to you. But before that, I thought there's a small part left in yesterday's class. That is the Bayesian something. Always happens after lunch. If you start speaking, there'll be something which will get stuck. Okay. So let's say the Gaussian prior. So we saw this P of x given y. So this will be the PPDF, posterior probability density function, likelihood density function, the prior density function, and this is the normalizing constant. Okay. So for the problem we are dealing with, so the probability of so for the problem under consideration, our parameter to be retrieved is the Q and T is the temperature. So the likelihood density function is Pt given Q is basically 1 by e to the power of minus chi squared by 2. Okay, where chi square is sigma 9.1 P measured J measured J. Okay, now what we are proposing is the P of x. We are proposing like this. Okay, so this is the mu P. So this is called the Gaussian prior. So when you do like this, you are saying that I am very much confident that based on my prior knowledge, it is likely to be around this region. Okay, with the spread of this. This is your prior knowledge. This is done even before your model is done or your measurements are made. This is basically your fundas. This could come from previous data. This could come from prior experience. This could come from your domain knowledge, whatever it is. But you're quantifying. So this is basically the belief system, which is the hallmark of the Bayesian. So you're incorporating or quantifying the belief. But now, so the P of Q is the prior is given by 1 by root of 2 pi sigma of the prior into e to the power of minus Q minus mu P whole square by 2 sigma P square. Are you getting the point? Therefore, so this is given by this. So this is given by this. So you have P of T given Q, which comes from the forward model, the measurement, and P of Q, which is your engineering intuition or your belief or whatever, intuition, whatever you say. If you combine these two, what happens now is you're getting, you can mathematically combine these two. So you're getting P of Q given T is nothing but 1 by 2 pi sigma square, e to the power of minus kappa square by 2 into 1 by root of 2 pi sigma P square e to the power of minus this one. Okay, divide by integral 1 by root 2 pi sigma square e to the power of minus kappa square by 2 into 1 by root of 2 pi sigma P square. Okay, e to the power of minus Q minus mu P whole square by 2 sigma P square dx. So, but you can see that this one, this one, this one, this one, all these root 2 pi sigma square will all get cancelled. Okay. It looks monstrous, but it is not very difficult. You can easily figure this out. Therefore, P of Q given T is given by e to the power of minus kappa square by 2 plus Q minus mu P. So this is for a single parameter problem. Okay. So please note that this is your new posterior probability density function. Okay. This is your posterior probability density function. Now you can see that. Watch my arguments very carefully. Am I audible? Just some thumbs up for the stoic silence in the class. Okay, all right. Now, because I'm going to get lost in, because I'll get lost in this because it's a topic of our research, right? So, if you ask me to speak again, I'll speak something differently. Okay, but it's not rehearsed. Okay, so this e to the power of minus pi square is basically the likelihood. Then this e to the power of minus this is basically the prior. So these are the product of two Gaussians is the Gaussian. That's why the e to the power of minus is getting added. What does it simply mean? This is e to the power of minus. So if you're generating a new sample for Q, for that particular sample of Q, you can always calculate the chi-square. But if this sample of Q is far away from the mu P, that means if it is far away from the mu P, this will be a high value. Therefore, so the whole thing becomes a lower value. Therefore, regardless of your chi-square, how your sample is different from mu P will decide the fate of the posterior probability density function. Therefore, if you give a prior like this, it can have a very, so this is called a very tight prior. So it is very informative because you are saying that it cannot, Q cannot lie here. You say Q cannot lie here because you are very confident. You can be overconfident. You can be arrogant also. So you have to be careful. But at the same time, if you give a prior like this, then it's a very loose prior. So if it's such a loose prior, then this mu minus sigma, whatever value you give here, all these will be the same. So it will not cause much difference to this P of Q given T. Therefore, the prior is figuring out the prior is an art. What you can do is, yesterday we generated a prior based on some funda. What was that? 500, 600, 700, 800, just some 10 samples randomly for the Q. And then you bracketed between 1200 and 1300. Then whatever map you got, that maximum A posteriori in your first level calculation, you gave that as mu P and 10% of that as sigma P. Now in the second level, you will do 1200, 1210, 1220, 1230, 1240. What is that? Watts per meter square Q. Okay. If you do that, then you will be in a much better position. If you can divide it further into 1200, 1201, 12, it depends on how rich you are. What is the computing facility you have? How much time you have? How much money you have for the computing? So therefore, this is in short the incorporation of prior. I wanted to do this because maybe yesterday you were a little fast. So for discrete values, so Q will be like this. Okay, Q will be sigma Qi e to the power of minus I square by 2 plus Qi minus mu p by 2 sigma p square. Okay. So the square is here. Divided by sigma of this fellow without the Qi. Is that okay? So this is I equal to 1 to m or whatever. So you sum it over all the samples. So what you do is you generate a Qi 1200 watts per meter square. For that you calculate the kappa square. For that you calculate this. Add these to e to the power of minus kappa square multiplied by Q. Okay. Do all this. And then now without the Qi, take the sigma, that will be the denominator. This is what Suraj showed you in yesterday's class. From this you can sigma p square equal to 1, sigma square equal to 1, all that. Okay, sigma q square. So you can get the SD, you can get the variance of the estimate and so on. Okay, so that formula is there, sigma q qi minus q square into blah blah blah, all that. Second moment. Okay, so this is the way of incorporating a prior. If you are saying that I will not use any prior, then this will not be there. Then this will just become MLE, maximum likelihood estimation. So the idea of a Bayesian comes here. It comes here, not only here. The idea of a Bayesian also comes in your bracketing. That means your bounds, whatever bounds you're giving. Yesterday we started from 1500 to 500 to 1500 for Q. That is also an information. Any information which is put into the system based on your prior knowledge, which will improve the outcome, is basically an incorporation of belief into the system. This is a proper quantification of the belief. Like that, you can give any other distribution. So this whole thing need not be Gaussian. You can work with non-Gaussian priors, you can work with non-Gaussian likelihoods and so on. That will be for a specific problem. The stock market crash or something you want to do, derivatives, you want to do analytics, business analytics, you may use a non-Gaussian process. That may be little involved. You may have to do additional courses in statistics, or you have to learn some more, learn on your own. And you will learn it if there is a need to learn it. Okay. Okay. So this brings us to the end of the first part of whatever today's lecture, where I wanted to talk about the prior. So now you know how to generate how to incorporate the priors. For the purposes of the exam and so on, we will tell you what the prior is and all that. And so that will be straightforward. But in an actual example, in an actual case, your problem, you will have to find out ways of generating prior. So I told you that this is a specific case where we generated prior for an unsteady conduction problem. It was way back in 2012 or 13. Okay, I asked Suresh to send that paper. I don't know whether he has done it. So is the prior idea clear now to you? So the prior is the hallmark of the Bayesian. Is the prior idea clear? How I've incorporated prior mathematically, that I have told you. And numerically how to do it. Is that okay?
Denominator of the discrete distribution, it will just be the excluding the Qi part.
No, excluding the excluding the correct. Excluding the Qi part. Okay, you want me to write?
Yes, sir.
So this is a sample. Is this okay now?
Yes, sir.
Okay. So let's say if one of the samples is mu p, what will happen to this term? If one of the samples is mu p itself, what will happen to this term?
0.
So it is 0 means it is giving the maximum weightage. At any other value other than mu p, this will be a positive number. Agreed or not?
Yes, sir.
So it will be e to the power of minus of the likelihood plus the positive number. So at any other, so this distribution penalizes you for taking values far away from the prior. Did you understand?
Yes, sir.
Yes, sir.
But the dynamics is basically how much is this value and how much is this value. This game is something which you have to play according to the problem. This is a game which you play according to your experience. This is a game which you play according to forward model and the measurement. So these two together is e to the power of minus. So finally you will get something which is the product of these two. So that's why it is a sum e to the power of. So then if your prior is good, if your measurements are good, model is good, your outcome will be good. What is your outcome will be good? If you get something like this, it is good. For example, if you get a, so if it is PQ of T, it is P. What is the use of this? If you get it like this, then there is no, even this can be answered, this can be answered, this can be answered, this can be answered, this can. Worse would be like this. So basically sampling. So you just to jog your memory. How to choose Q1, Q2, Q3, for example. So one is called, we call it as offline. This is pre-assigned. That is, it's just pre-assigned. You just divide the interval into so many parts as you like. So this is yesterday's example. Okay, this is yesterday's example. Now there is yet another method where you just do a dynamic generation of samples. Okay, under this dynamic, when you want to study the dynamic generation of samples, you have to know what are the methods available to do this. The first is a Markov chain. In a Markov chain, new sample depends only on the old sample. The new sample depends only on the old sample. So it is a memory-less process. Okay. So in that, so if you combine this Markov chain with a Monte Carlo, this is a Markov chain Monte Carlo. What is a Monte Carlo method? A Monte Carlo method is something where you generate some samples using random numbers. Instead of just pre-assigning, you will just have a random number. Use a random number. Okay, just say the first value is 500. Q is equal to 500. Second value is 500 plus 1500 minus 500 divided by 1500 or whatever into some random number. So that will be 7. First random number is 0.2 means next sample will be some 700. Then third sample could be 500 plus blah 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 into second random number, third random number. So that is, so if you generate this randomly, it is a Monte Carlo. You can use a Monte Carlo simulation, Monte Carlo integration, and all that. What is this Markov chain? In a Markov chain also, in a Markov chain Monte Carlo, you generate the samples using random numbers, but it is a memoryless process. What you do is everything is not linked to the first number of the second. Okay, from the first sample, using random number, you go to the second. That is a Monte Carlo. What is a Markov chain? When you come to the third, you forget the first. From the third current sample, you can do something else. You can use a Gaussian distribution for each of this, but the current sample becomes the mean. Okay, are you getting the point? I will make it very clear to you. Okay, there are many ways of doing it. In this Metropolis and Hastings, Metropolis and Hastings were the people who first used it, who first demonstrated its use. Okay, in a problem where you want to work out the in a Bayesian approach. Okay, they were the first to show it in a Bayesian. What is Monte Carlo? Monte Carlo is the use of random numbers and generating the samples dynamically. What is a Markov chain? Dynamically generating a samples, but a new sample depends on the old sample only. Then what is a Metropolis-Hastings Markov chain Monte Carlo? Using this Markov chain Monte Carlo in an inverse problem, or in a way in which the sample can be not only an inverse problem, any problem where you want to decide whether to accept the sample or not. That is the Metropolis-Hastings algorithm. So basically it is like this. Let's say that one way is like this. Of course, Suraj today will show some other method. So what I can do is, for example, let's say it is like this. Okay. So the current sample, okay, the current sample, the old sample or the current sample is xi. You consider a Gaussian distribution around the current sample and take an appropriate sigma equal to 0.1 of xi. Now you are saying that the probability of getting the I plus 1th sample is 1 by root 2 pi sigma square e to the power of minus xi plus 1 minus xi by 2 sigma square whole square. Are you getting the point? Now what you do is, you are saying that the new sample is pulled out from this Gaussian or the old sample. So for the generation of the new sample, what you do is, you just take the Gaussian, generate a random number, let's say 0.2 or 0.3. So left hand side 0.3 is known to you. Sigma already you know is 0.1. This could be 0.05, whatever, some value. So you already know that 0.1 of x1. So this is known to you. This you are generating a random number. If you solve this quadratic, xi is your old sample. So if you solve this quadratic, you get two values of xi plus 1. So from xi, you are able to go to the xi plus 1. This is the way of getting it, pulling out a new sample from a distribution. This is computational statistics. Now, since it is a quadratic, you can say that random number less than 0.5, one root. Okay, what is that root? That root is less than the current sample. I don't know. Greater than 0.5, other root or something. You can generate a random number, decide which of the, or you can say there are two roots. The lower root will be taken if the random number is less than 0.5. So already you have generated two random numbers to decide this. Okay, first random number is to pick and choose this probability. The second random number is to pick and choose. Now the Metropolis-Hastings is coming like this. Okay, now watch the arguments very carefully. So there is a p of y given xi, call it as p1. There is a, you can also calculate the p for xi plus 1, call it p2. Is that okay? What is this? I made a mistake, so it should not be this. So please calculate your posterior density function for the current sample xi and the newly proposed sample xi plus 1. The newly proposed sample is not yet accepted. We are in the process. Calculate P1 and P2. If P2 is greater than P1, that means the probability of I plus 1 posterior is higher. Will you accept the sample or not? Will you accept I plus xi plus 1 or not? Please tell me.
Yes, sir.
Huh?
Yes.
Accept. Okay, good. Very good. Accept xi plus 1. What is common sense tells you? If P2 is less than P1, then the new sample is bad. Therefore, you reject it. The Metropolis-Hastings, they are stuck, guys, because they said that reject as xi plus 1 with the probability. What it means is, initially when you're doing a random searching, you don't want to get stuck in a local minimum. So sometimes a function can be like this. Okay. So if it goes in this direction, then you always the solution will converge to this. Let's say this is y of x, only a single value, single variable. So if you start with a wrong initial xi, then it may decide that you. So if you allow only when it goes up. Okay, let's say if you want to do a minimization problem, only if y goes down, if you accept, then the solution may get stuck here. How will you go to this? Therefore, initially when the algorithm is starting to solve the problem, you allow even bad fellows. Okay, don't decide the grade of a student based on quiz 1 or one quiz alone. You say that one quiz I will give you the grade. What will happen to you? Somebody can just figure out and then he can crack in the end sum. No, that's why initially itself you should not say that oh he's bad, so we completely throw him out. That is not good. So Metropolis-Hastings said that you reject with a probability. What is that probability? They introduced a new term called acceptance ratio. So there's something called A, acceptance ratio. So what is this acceptance ratio? So this is this thing. So they say A is a function which is a minimum of 1 and P2 by P1. Okay. Generate a new random number. Let's say U3. Okay. If A is greater than U3, accept xi plus 1. A is less than U3, reject xi plus 1. So one iteration is complete only if you accept a new sample. So if you have rejected, you will go back and generate the first random number and pull out the new sample from the from the Gaussian. Proceed with all these steps. You will continue with all these steps till you get a new xi plus 1. So now what you do is, so if this is P of Q given T, so you will do like this. It may go like this. Go like nothing is pre-decided. Yesterday, what you did? Then you found out. So this sample was something which was beyond you yesterday. But now I'm saying first sample to second, third, fourth, it may go like this, it may go like this, but it's okay. But now you know that we are engineers. We know that the answer is somewhere here. Okay. So this means you're working out. You're working out the posterior. You work out the posterior in an actual sample. Suraj, how many samples are you taking? We take 5,000, 10,000, 20,000 samples. But now what is the effect of initial guess? If the initial guess is far away from the solution and this thing, it may take a long time. That's okay. But it will have a bias. The Markov chain has a bias towards the initial guess. So if you generate 1,000 samples, the first 10%, 10 to 20%, 10% is called burn-in. So you don't use the first 10% of the samples for calculating the posterior district, for calculating the post-processing the estimators like mean and standard deviation, so on. So this is what this is that high funda Metropolis-Hastings base mark. So the Metropolis-Hastings, this idea of not rejecting something outright, this is supposed to be one of the most 10 powerful algorithms ever developed by man in any subject. If you just, it's not I'm saying that, you can check the Google. It is one of the most, because it's completely lateral thinking. It's not that, okay, if it improves, I'll accept. If it doesn't improve, I'll reject. That is everybody, that is a beaten path. Everybody takes that path. These fellows said statistically, we'll use random numbers and culprit and allow. If somebody goes and somebody doesn't study properly, it's okay. We'll give him more chance. We'll give him one more assignment test. We'll give him quiz. Suddenly, he may start liking the subject and he'll do well. So I think it makes sense. It makes sense to do this way. Therefore, the chance of missing the correct answer is very less in a in a MCMC method. However, it is computationally intensive. Since many of your data science guys, this is like you're taking Kaju Katli or Badam Halwa for you, because this is ideal for programming and this is ideal for using in data science. Even if it's not an inverse problem, please try to use the Markov chain Monte Carlo. Absolutely powerful algorithm. You can use it for any problem you want. So in statistics. So somebody who does all this is called a computational statistician, rather than somebody who says P of 1 equal to P of A intersection B A union B. Somebody said yesterday, no, all those theorem guys, they are all the probabilists. The statistician, some people will work with data, will work out the posterior, they'll work out the generate the sample. They will do a lot of computational work. They'll do measurements. They'll do all this. So these are the real guys. Okay. Pollsters, exit poll, opinion poll. There are many people. They all do use some models like this. They will use some prior. They will use some. They will take some data and proceed. All right. Now, is the idea clear? So we will solve the problem. Once we solve the problem, that you have 20 more minutes. That will become a little more clear to you. We'll give that to you. Of course, things will become very clear to you on the day of quiz 2. Suppose you don't miss it right, you don't get it right in the quiz, we'll have one more chance. You will get it right in the end sem. All right. So we go to the problem now. If there are any questions, you can shoot as Suraj gets ready to show the solution. Suraj is using some other distribution. He is using a uniform distribution. We will tell you what that is. That is easier. I taught it the more high funda one. Okay. Suraj is using a slightly lower. Suraj, just show the solution. Are you there, Suraj?
Yes, sir.
You show the solution. He is using a less difficult, taking a less difficult approach. Okay, consider the one-dimensional blah, 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 blah. Okay, so consider the one-dimensional, yeah. Okay, all that, fine. We know this. Go to the next one. Please take down the algorithm. Please take down the algorithm. Hey, Suraj, you are showing this algorithm, but in the demonstration, you are using some other method, right?
Yes, sir.
Okay. This algorithm also, we can give it to them as PDF. PDF as notes to them. Okay. Somebody wants to write down, please write down. Initialize x of 1. For I equal to 1 to m, generate a random number. Calculate the next sample. If u is less than a, accept. Else go to step 2, where m is the number of samples. Okay. So what is u1?
U1 is a random number, sir. U1 is random number, sir. Random number.
Random number. What is that? Q new is q plus. What are you saying? Q new, q plus sigma into. There you're again saying that it is not the. It is not correct, Suraj. What you're saying is not correct.
Sir, Q is a next sample, sir.
Yeah, but in that case, you should not use the Gaussian on the right side, right?
This one, sir. Yes, sir. This one for acceptance, sir.
For acceptance. Okay, for acceptance. Okay, for acceptance. All right. Okay, very good. So what he is saying that P of new, but why are you using
this is without prior, sir?
Without prior.
Yes, sir.
Yeah. Okay. See, there it's very nuanced. So don't get confused. So don't worry about the dialogue with Suraj. Okay. So Suraj is doing PhD in inverse. So I am in this field for many years now. So what we said now was, I put P of 1 and P of 2. Suraj is showing the likelihood instead of the posterior within the box. Why he said he's doing that is he's using it without the prior. Okay, without the prior, the likelihood will be equal to the posterior. That's why he did that. But if you have to be clinically correct, okay, Whatever I've written on the board is final. Okay. So this, whatever Suraj is showing now, is strictly valid for a situation with no prior. Is that correct, Suraj?
Yes, sir.
Okay. So what you do is generate a random number and keep it. That is you. Calculate the new sample. The new sample will come from the old sample. But Suraj has a simple way of generating that, which you can follow in the exam also. I will tell you that will come next. Now, please calculate the probability new. That is P2. Okay. Already P1 is known to you because from the first sample, you can find out the likelihood. Calculate the likelihood for the second sample and then use this acceptance rejection ratio. A equal to minimum of 1, P new grade 1 of P new by P old and this thing. It looks very confusing here. But once you solve the problem, once you start solving, it is very, very simple. Okay, come down, Suraj. All right. Okay, now forward model d square t by dx square equal to 0, t equal to ax plus b. So finally, you put it in this form. The only unknown in the problem is q, given 5 measurements. Okay, random number table is given to you. So please use the first 3 columns for generating the u1. For the generation of new sample based on delta from the current sample, use the first column. Random number 2 to decide whether you have to go to the right side or left side of the current sample. Okay, because he is using a simple distribution. It will become clear to you in 2 minutes. Third random number is that u3 to decide whether to accept or reject. Now go to the Excel sheet, Suraj.
Yes, sir. Already, sir.
Already, yeah?
Yes, sir.
Okay. So all of you just look at the random numbers given to you. Look at the first column, second column, and third column. The first row will be u1 is 0.01213, u2 is 0.8988, and u3 is 0.5788. Let us say that the initial sample q is 1200. So that will be the current sample. The standard deviation is 10% of the current sample is 120. Okay. Here, u2 is greater than 0.5. So what he did was, instead of using the Gaussian, simply Suraj took a very simple approach. What did he do? He's saying that the current sample is equal to old sample plus random number into the standard deviation. Okay. All right. So what is that random number? The first random number is so small, 0.001213. Therefore, his current sample and the old sample are very nearly the same. Doesn't matter. We are just demonstrating the technique. Okay. Wait, Suraj, just go up. There are several things in this first few lines. Now, the second random number is greater than 0.5. So what are we saying? Since the second random number is greater than 0.5, that sigma into u1 will be added to the current sample. If the second random number is less than 0.5, the q new will be q minus sigma into u1. Is that understood? Somebody can tell me. I'm not able to see you. If you understood, you say yes.
Yes, sir.
So all the drama, please note that all the drama before the tabular column is to just generate Q2. That's all. What the Monte Carlo, Markov chain, all that is doing is basically to generate a new sample from the old sample. Yesterday we just said 500, 600, 700, 800. Now we are doing hard work. We are using probability and statistics to generate a new sample. Once you have Q equal to 1200, you can calculate T1, T2, T3, T4, T5, T6. You can calculate the error, square of the error, sum of the square of the error. All those things you can work out. Come down, Suraj. Okay. Now, he has calculated all that. P old is 8.6 into 10 to the power of minus 27. Very small. P new is also, P new is P 8.96. Okay. P new is greater than P old. Therefore, the new sample is accepted. Okay. But what is the answer? Answer is from 1258. So anyway, we are going in the right direction. Okay. Now, from 1200 in one iteration, we came to 1200.1456. So some iterations can be very frustrating, but this first iteration was not very impressive, but it's okay. Please note in the exam, so we know how much time it will take. We'll ask you to do 5 to 7 iterations. Okay. 5 to 7 iterations means 5 accepted samples. You should keep on working out till you get 5 accepted samples. So this is iteration 1. Now 1200.1456 will become the current sample. Go down, Suraj. Okay. Current sample is 1200.1456. Go to row number 2. the new set of random numbers U1, U2, U3 are coming 0.499, 0.282, 0.735. So what Suraj is doing is sampling so the new sample, so this will be Q new. So this will be right, Suraj, correct, right? You're not using 3 sigma.
No, sir.
Okay, so this is called a uniform distribution. He made it very simple. What I taught you was from a Gaussian. So in the exam, if it is going to be comfortable for you, use a uniform. Some people you want to use a Gaussian, I would prefer, but I will not give lower your marks if you are using a uniform distribution. Uniform distribution is some low level, but it's okay. So that means it will take a lot more iterations to convert. Now let's go to the second one. Old is 1200.1456. Sigma is why is he sticking to sigma 120? Sigma 120 is 10% of Q. You should not because you should not cause wild changes in your new sample. That's why actually Suraj, you should not do this. It should be 10% of current sample, na?
Yes, sir. 10% of current sample.
But you are using 120 itself.
Yes, sir. In this case, I
Okay. So students, please note always the sigma should dynamically change. Sigma should be 10% of current sample. If somebody wants to do 12% in the exam also, it's okay, but don't do 200%. Okay. If you feel that you have to be unique, just use 9%, 11%, 12%. But tell us what you're doing. You can always check it. Better if everybody takes 10%, it's easy for us to evaluate. All right. Now, second random number is less than 0.5. So what Suraj is saying is the Q new will be equal to the Q old 1200.1456 because using this minus sigma into the first random number. So you got a sample which is 1140. So please note that the new sample can lie only between 1080 and 1320. Is that clear? Can somebody confirm? New sample can lie only between 1080 and 1320. Is that understood?
In the expression that you wrote on the board, there you had not multiplied by U1. Why is that?
What?
In the expression that you wrote, there the sigma is not multiplied by the first random number U1.
No, but that was because this is the uniform distribution. Therefore, the distribution is like this. So for this, you have to multiply by for you. In my case, directly you can get the x by solving the Gaussian equation. Is that okay?
Oh, okay, got it.
You can direct. That is a more involved. That is a high funda method. I would prefer that. This is a very simplistic, but it's okay. But you can easily understand in the class. I think what we did, why we are doing this. If I start with Gaussian, it may be very difficult for you to understand. But what all of you have to understand is how you are proceeding to new sample from the old sample by using the idea of random numbers. And also, you already forgot about the first sample. We are now considering the sigma of the second sample, mean of the second. So the first sample might have caused the second, but we are no way. See, everything has to change. Everything is afresh. It's a new distribution. Therefore, your change from first to second sample can be completely different from second to third sample. That is the Markov chain. That is a memoryless process. Because it is memoryless, what is the advantage? The bad memory of earlier samples, the bad memory of a wrong start, or what we call it as in English we call it as a faux pas, right? A bad start, a faux pas can be erased. So some people they really thought about all this, guys. Our forefathers. Now you got 1140. Again, you do all the drama T1, T2, T3, T4, blah blah blah. Come down. Some of the residual. Suraj, go up. Now, and the P new is much lower. Now it is worse off because you know the answer is 1250. Go up, Suraj. The answer is 1250. Go up. The answer is 1250. No. Come down. Next. Show the sample. We went in the wrong direction to 1140. Therefore, the probability is showing up. See that. Come down. So the probability is cupping. So it is P nu is, but still you have to, because it is Metropolis-Hastings or Gurujis have said that don't reject it. We will check it with a random number. A equal to minimum of, what is minimum of 1 and 4.179? It is 4.179, blah, blah, blah. Now A is less than U3. Okay. Therefore, you reject the sample. Okay. A is less than U3. You reject the sample, which is very good. That's the way we have to do it, because we know that it is not in the right direction. Okay. It is so easy to find out in this problem because it's one variable. When several variables are there, you don't know in which direction you are moving. So you retain this. Now you cannot say that you completed second iteration. You complete the second iteration only if you get the third sample. Go back now. Go back to your distribution. Come down to that. Okay, iteration number 3. Get the new set of random numbers. Okay. Please note that U1 is the first column, U2 is the second column, U3 is the third column. Just keep it fixed. You can ulta it, but you don't horizontally go, because the three things U1, U2, U3 are separate things. Decisions are, you're taking separate decisions based on this. Okay. Now, volt is 1200, sigma is 120. Any doubt?
So like, can we take only one random number? Like
Then do what? No. Then how will you decide whether you have to add or not?
So like U1 equal to U3 equal to U3.
Yeah, that is not good. So this gives more variety. You can try that also. That will become very slow. This is nice. Use 3 random numbers. There should not be a connection between the random numbers. That's not a good idea. You are taking different decisions. No, better to have more random numbers. Okay.
So, when we are suppose rejecting one particular sample, as we did in the previous case, even then the random numbers U1, U2, and U3 have to be like generated randomly once again. Or
correct. It's because the random numbers don't have any connection. You can't put a pattern to the random number. So it's just go to the new random number. That's all. Third row on the table. Please use this table in the exam also. The first set was first row, second row. Now you came to the third row. Third row, column 1, column 2, column 3. Correct, Suraj? Is that correct? What I'm saying?
Yes, sir.
Is it clear? Don't stick to the old random number. Change the random number. No problem. Okay. Now again on to 1020, blah blah. He got 1187. Come down. He got 118. And is it accepted? Now the probability is increasing. Therefore, is a P nu is 0.99.
Yes, sir.
Go up. What is the sample? 1187 is the answer. Come down. There may be some mistake in this. Come down. Okay. Anyway, come down. I can't believe that P nu is 0.99. Because 1 is 10 to the power of minus 27. How did you get 0.9? So just check this number.
Okay, sir.
I think it is wrong. Okay. Anyway, even if it is wrong, the beauty is it will correct itself. Go to the next sample. Yeah. Okay. Now iteration 4, we have come to 1254. Come down. Now it should converge. So 0.99. So now we are able to see that it is increasingly getting accepted because Suraj.
Yes, sir.
So I think please check the previous iteration before sending to the students. I think there's a problem with that. Okay. Now you have come to a good stage where you are in now 1254. Come down to the next iteration. Okay. So now it is going very slowly. You see 1254, it becomes 1265. Come down. Yeah, so you're getting a probability of 0.9 and it's getting accepted. That's all, or one more iteration. 1360. Now it goes to 1356. Again, this should be rejected because you're moving out of the solution. Come down, if my hunch is correct. You're accepting this also. Suraj?
Yes, sir.
And then? When will it turn?
Yes, sir.
That's all.
Yes, sir. Up to 6 iteration.
Yeah, but if you do more iterations, what happens?
It will be rejected, sir, I think, sir.
It will be rejected. So it will again get rejected. So finally it has to come back. What is the answer?
No, sir. 1265.
So this is basically now he has worked out the table, and so
Can show MATLAB code, sir, also?
you can show the MATLAB code. 1 second. I have a meeting at 2 o'clock. So what you can do is, so now he has generated the PPDF. Okay, so based on first sample, second sample, third sample, and so on. So now for each of the samples, he has got the posterior density. You can work out the previous. Now please note that for 6 samples, we got 1200, 1200, 1827, 1187, 1254, 1265, 1356. Yesterday we got 500, 600, 700, 800, 900, 1000, whatever, or 1200. So the samples now are dynamically generated. Same tabular column, except that the Q was generated using the Markov chain Monte Carlo method. Now show the posterior in the form of a plot. You have a MATLAB code?
Yes, sir.
Just show it quickly, 2 minutes.
Okay, sir.
Sir, in your method, when are we generating second random number, sir?
No, why are we generating the second random number is basically
when
the quadratic. Wait. I understood your question. Allow me to talk. I got your question. So there is a x squared minus 2 sigma square, no x minus. So it will get 2 roots. Use the random number to decide which root you want. Is that okay? You understand?
Yes, sir. Yes.
Okay. I got your question because I got these questions before also. So now you please see how many samples are there, Suraj?
1000, sir.
1000 samples for this problem. Suraj has written a MATLAB code. Now you can see the answer is about 1250
I am
watts.
also generating sample from Gaussian distribution.
So he's also generating the samples from Gaussian distribution, my method. Did you use the second random number to choose this thing? How did you choose between the 2 roots of the quadratic?
Same, sir. Like greater than.
Same, greater than some random number. Okay. So thank you very much. So this brings us to the end of my portion of inverse heat transfer. So 30 classes. I hope I conveyed the message to you. The idea of marrying measurements with a forward model and a prior, whatever framework. If there is no prior, you will do classical statistics, least square regression, nonlinear regression, so on. So this is a way of moving forward instead of just trying to solve only the forward model. Observe the phenomena, take some measurements, marry, mix and match. You can get much more information. So this is the whole idea. So I hope it's appealing to you. So proceed.